And I'd like to start by thanking the organizers very much for inviting me. My first visit to Sweden, and it's a great pleasure to come visit this very beautiful and very civilized country, so thank you. So I'll be talking about a collection of papers, and also a couple others will be mentioned that aren't here. And I'd like to start out with what I think is a plausible viewpoint on the state of physics today, so to speak. And that is that the black hole information paradox seems to me that it could be of comparable importance to the paradox of the classical instability of matter. The classical instability of matter, of course, was central in discovering quantum mechanics, and it seems that black hole information, at least the paradox of black hole information, may well be central in discovering the next framework of physics. Let me just begin by reminding you very briefly the nature of the paradox. And of course, I don't have time to review it completely, but let me just state the essence of it, and that is that apparently we must abandon a cherished principle of physics in explaining what happens to black hole information. Of course, there's what Hawking originally advocated, that unitarity and consequentially energy conservation are abandoned in the process of abandoning quantum mechanics, or you need to abandon stability if you believe in a remnant scenario, or you need to abandon macroscopic locality on the scale of the black hole if you believe that information escapes from the black hole. And it's certainly become widespread belief in today's community that this latter principle is the one that goes. But if that's true, if indeed there is some fundamental non-locality in physics, there are some very interesting questions, like what is the mechanism for that non-locality? What's responsible for it? How is Hawking's argument for information loss evaded? Where does general relativity plus local quantum field theory actually fail? In what regime? Another way of stating that question is to ask the question, well, what is the correspondence limit for whatever the new physics is, where it matches on to existing local quantum field theory plus general relativity? And of course, there are proposals for where that correspondence limit is that are, well, have been discussed. Let me just mention what some of those are. There's the well-known proposal that the physics needs to be modified at Planckian curvatures, but there are others. For example, there's the suggestion of the string uncertainty principle, going back to Gabriele and Gross, that there's an extra term in the uncertainty principle that has to do with string theory. There are, of course, suggestions that Lorentz invariance somehow gets modified, so you have perhaps modified dispersion relations or what have you in new physics when momenta reach the Planck scale. And then there are also suggestions that there could be holographic or information bounds, and that you need some new physics when describing an amount of entropy or information that exceeds the area of surface containing the region in question. So these are all proposals that have been discussed, and I'll come back to one other suggestion. But in this talk, I'll be exploring some issues which I think shed some light on these basic questions. And I'll begin with the role of string theory, which I think is an important question. What does string theory tell us about these basic questions? So if there is some non-locality in string theory, I think we'd expect to see some evidence of it in high energy scattering. And so, in particular, you could ask whether some new non-locality in physics comes from the fact that strings are extended objects. That's certainly something that's been considered, and so one question is extendedness this mechanism? And so the basic picture would be, for example, in a high energy collision of two strings, you have enough energy that you could produce very highly excited and long strings, and that this might somehow have something to do with non-locality. Now this picture, if it's correct, actually raises some interesting questions. One is, what does this have to do with black hole formation if you have highly excited strings that form in a collision? Over the years, I've been asked by very prominent physicists whether this actually could somehow prevent black hole formation because it prevents you from concentrating enough energy into basically a horizon-sized region. Or on the other hand, you might take the point of view, which I think would be in keeping with some of the things Lenny has said over the years, that somehow strings getting spread out like this might have something directly to do with black hole formation, and may, in some sense, capture black hole formation. So we'd like to go after those basic questions, just to say a little bit more about these excited strings that can form. So you could, of course, make the observation that the energy of a string is proportional to its length, so at high energy you can make very long strings. So the first guess is it's just simply this effect that leads to excitation of a very long and non-local object. And indeed, in a sense, this is what is responsible for this extra term in this so-called string uncertainty principle. And if there were a term there, that certainly is something that is not, well, you don't see it in local quantum field theory, so it's some form of non-locality. And moreover, this basic picture that strings can get long has been proposed to apply to this black hole information paradox by Lowe, Polchinski, Susskind, Berlasius, and Uglin. And so it's important to try to investigate more closely this picture that strings can get long and highly excited. And let me just begin with tree-level processes in the high energy limit. And so you can write down the amplitude for high energy string scattering, say graviton-graviton at high energies. And compare, for example, that amplitude to just the scattering amplitude at tree level for graviton, single graviton exchange. So obviously there are some important stringy modifications, but a first observation is in comparing these two tree level amplitudes, you don't really see a role for states that correspond to long excited strings. And there are reasons for that which I could explain, but it has to do with open-closed duality, for example. And in essence, you don't see this kind of long string modification to the formula directly here, but you do see some important stringy modifications in these exponents and the gamma function and so on. And those modifications set in at momenta transfers of order the string scale. And so let's start by asking what role those modifications play. So stated that. And so in order to actually investigate the role that these modifications play, in particular, you could think about, say, looking at how scattering behaves as a function of, well, instead of S and T, energy and impact parameter. I'm interested in this parametrically high energy regime, much greater than any relevant scales, the Planck mass and everything else. And so the fact that scattering gets important corrections at T of order 1 in string units suggests that at impact parameters that correspond to this power of the energy, you could have important stringy corrections. I'm going to always work in D non-compact dimensions. So if I, for example, fix the energy and lower the impact parameter, you might expect when I hit this line, I reach some regime where stringy effects are important. So that's certainly a possibility that's suggested by the tree level amplitude. And if so, this would likely be interesting and significant for locality if you had some important stringy corrections at this kind of impact parameter. But to check if that's indeed the correct physics, one should also examine higher order corrections to amplitudes, specifically loop diagrams. And so let's move on to do that. So we'll compare the loop amplitudes. And here, quite a lot of work has been done over the years. Very seminal work by Gabriele and his colleagues some number of years ago, Zinich and Solday. And then there's this recent paper where we looked at some of the issues with Gross and my student Martin Rana. And so we're interested in the structure of loop amplitudes in the high energy limit. And at ultra high energy, it appears that the amplitudes that dominate are actually those that correspond to the iconal, the iconal amplitudes. Here I've just pictured gravitational exchange, but of course we could have strings in place of these things that have been drawn as graviton propagators. And you can figure out the structure of these amplitudes in terms of the string tree level amplitude, the one I had on the slide just a moment ago. It's a, simple matter to figure out how the propagators and so on get put together. Again, these are just crossed ladders, so there's no interaction there. These are just exchange of string states or gravitons. And of course, here we have a set of momenta being exchanged to kj, and they have to sum up to the total momentum exchange, which is q. So that's expressed in that delta function. So that's the in-loop diagram. And first of all, let's ask the question of are string corrections in here, those that I was just referring to, are they somehow important? And to do that, let's just look at the region of the momentum integral. Actually, I think, there's the integral sign. The region of the momentum integral that dominates this amplitude. And here are actually for example, the dominant string corrections to the amplitude in the exponential that I had referred to. But it turns out that because of the 1 over kj squared here, the dominant contributions to this collection of integrals come when the momentum transfer q is equally distributed roughly between each of the exchange lines. So each line has wrong button. Okay, so each line carries a fraction 1 over n of the momentum transfer. And that means, in particular, that these corrections, again, the dominant string correction, actually are quite small. The effects due to string theory are quite small. Roughly speaking, the momentum transfer likes to spread out and soften each of the vertices. And so you have a picture where you have a number of fairly soft interactions, as soft as they can be, and that means that the string corrections are not so important for high loop order. So that's what I've just stated, that at high loop order, string corrections get smaller. But of course, the important question then is which loop order dominates the actual physical amplitude? And you can sum these diagrams, the iconal series, and get a representation that basically involves an integral, Fourier transform of the exponential of an iconal phase. And that iconal phase takes this form, e squared over the impact parameter to the appropriate dimension-dependent power. And since that's an exponential sum, of course we know what order dominates that sum. The order is given by the phase. That's the dominant order, and so if we're interested in a regime where t is of order -1, we just have to replace the formula for the impact parameter in terms of the energy for that value of t. And we find that the order diagram that dominates this sum is actually something that grows like a tower of the energy. So it's a very high loop order that dominates the sum, and their stringy corrections basically are expected to be quite small. So, in fact, this suggests that string corrections are not so important at t of order the string scale. And, in fact, the basic picture that emerges is that we are simply describing accurately scattering in the iconal approximation, which is essentially classical scattering. Classical scattering can be described as a collision of two Eichelberg-Sechsel shock waves. And Gabriel and his collaborators have performed some checks on this picture. So this is what we're talking about, where those represent the two strings. And the question then becomes, for example, do we have black hole formation in the context of the collision of two such Eichelberg-Sechsel shock waves? And the answer is classically yes. But, of course, and again, this is something Gabriel and his collaborators have pointed out in the study, when you consider the fact that these objects are strings, they can get excited in what's called diffractive excitation. And you're back to the idea that that might somehow play an important role in the process. In fact, the amplitude for these two strings to collide and not get excited at an impact parameter that corresponds to the Schwarzschild radius is actually exponentially small as a power over the energy. And so that suggests that you might be back to a picture that looked very similar to the one I drew earlier, where the string becomes highly excited in the collision. And if that's true, then, well, maybe we're back in a situation where we either don't have a black hole or where we have some dual description, perhaps, of a black hole. And another idea that comes from this is even if we do have a black hole, maybe somehow the string excitation has something to do with carrying the information away from the black hole internal states. And that's something Gabriel suggested a couple of, 3 years ago. But contrary to this picture, let me mention there's some intuition that the string should only get spread out like this basically after the two shock waves collide by causality. And so one should ask that question. But the problem with trying to nail this down, of course, is that string spreading is a notoriously sort of fuzzy concept. So you have to be a little bit careful. Okay, so let's ask the question, try to ask it more sharply, where is the string? And this kind of question has been explored by Karliner, Klebanov, and Susskind, and the answer is it depends on the process that you're considering. If you're thinking about the strings that are the electrons in your bodies, they are not spread out all over the universe. They are in your bodies. And so if you ask low-resolution questions, strings don't get all spread out. But if you do instead try to ask very high-resolution questions from the string at very short distance scales, ultimately strings do get very spread out. And so really, in order to answer the question, how spread out is the string, you have to think about the dynamical process in question and check carefully how spread out is the string getting in the process in question. So as a test of this, we need to explore this collision of these high-energy strings, and we can't treat analytically the full collision problem. But these string spreading effects persist even in the simpler case where you just have a string colliding with a single Eichelberg-Sexual shock wave, and you neglect the back reaction of this string on that one. And so we should be able to examine and understand this effect quite well just in this case where we're neglecting that back reaction. That's what makes the problem hard. So we'll go ahead and explore this situation here. Neglecting back reaction, and of course the Eichelberg-Sexual shock wave has a metric of this form. It's basically flat on two sides of the shock wave. Here mu is the energy, is a transverse potential, and basically, at least in an ideal limit, just a delta function shock wave. And so the question is, what does string propagation look like in such a geometry? And the nice thing about that problem is that it has a natural light cone structure, so you can easily study it in light cone radiation, as has been done some time ago by these authors. And so it's quite simple to set up and actually do explicit studies of the nature of the dynamical process. And so what we'd like to do is compute for an incoming unexcited string, say the mean squared deviation of that string from its center of mass. How spread out is it? In order to sensibly do that, you really do have to put in a worldsheet cutoff. This is just as in ordinary flat space. If you want to be able to say that the strings in your bodies are not spread out over the whole universe, you need a string worldsheet regulator. And so one uses that, but then you ask the question, can I choose that regulator in the context of the process in question? So that I have sufficient resolution, but the string is not spread out. That's the basic approach. And I don't have time to go through the full calculation, but let me just state what the findings are. And the findings are that what happens is, well, the basic sort of classical picture is essentially true. You have your shock wave. The string comes along. It's quite small because you're moving in flat space. It hits the shock wave. It gets a tidal kick from the tidal force of the shock wave. Then it begins to spread out. So initially, it's not very spread out. It's only asymptotically very spread out. And of course, there are these effects due to the cutoff and so on, and you have to be careful. There are these extra logs in here which are not classical. But even with the logs here, and with this cutoff-dependent term, and you have to choose the cutoff less than the time at which you're trying to resolve things, even with those effects, you find that this basic picture is correct, that the string at early times is not very spread out due to this tidal string excitation. So that means that you appear to have a picture where you can control the string spreading, and for small times, the string is indeed inside of a trapped surface that forms. So that means that the string behaves approximately locally during the collision, and a black hole indeed appears to form. And so let's ask what conclusions we can draw from this set of observations. So the first is that now there is no evidence that string effects prevent black hole formation. And let's look at the picture of what string scattering should look like as a function of energy and impact parameter. And so first you have at very large impact parameters for a given fixed energy, this tree level exchange, Bourne excitation. And then as you go to smaller impact parameters, you get in the regime where these higher loop contributions are important. You get into the regime of iclinal scattering. Then you get into the regime where the strings start to become tidally excited as you're coming down in impact parameter. But then ultimately you get into this regime where it appears that gravity really truly gets strong at this curve, given by f power of e. And that's the regime where you expect to have essentially black holes. I should also mention there's a lot of potentially interesting physics in a regime down here where you really have stringy effects below the so-called black hole string correspondence point and scales to the smallest integration are comparable to the string length and smaller. But I'm interested again in this parametrically high energy regime. Okay, so that's a plausible picture for what's going on. And I just want to emphasize that this strong gravity boundary black hole formation actually corresponds to breakdown of the gravitational loop expansion. For example, if you look at the relative contribution of these two diagrams, it's easy to see you have 2 extra powers of the gravitational coupling, and in fact this is an expansion in the Schwarzschild radius over the impact parameter. So when the impact parameter reaches the Schwarzschild radius, this sum is 1 plus 1 plus 1, it diverges. And so this is a question that I think is very interesting to ask. How would string theory deal with this? In what sense is string theory a complete theory of quantum gravity? It seems to regulate these diagrams one by one, but the whole sum looks like it's badly divergent. Okay, secondly, there's no obvious precise notion of locality in this story. When we study scattering, locality is encoded in various bounds. So for example, there's the Froissart bound on the total cross-section, and there's the Saarland-Martin bound, which is a lower bound on the scattering amplitude at fixed angle. Those are how locality, these are sort of our best notions of locality in the context of scattering. We're studying scattering, so what are our expectations from string theory? Our expectations from black hole formation. Our expectations from black hole formation, strong gravity, are that the total cross-section grows like a power of the energy, contrast, and the elastic cross-section for 2 to 2 scattering actually falls too fast. It falls like the exponential of a power bigger than 1. Okay, so there's no clear indicator of locality, and certainly this contrast is suggestive of non-locality. Okay, thirdly, so scattering at sufficiently small impact parameter appears dominated by strong gravitational effects. And so that suggests that if there is some fundamental non-locality, it has its origin in gravitational dynamics as opposed to, say, string extendedness. That should be obvious from the arguments I've presented so far. Let me just make a side comment. Of course, often the issue of renormalizability in gravity is emphasized, but perhaps the more fundamental issue somehow is really unitarity. And in fact, in the context of knowing that you need to extend the electroweak theory and, say, introduce the Z boson or the Higgs boson, you could phrase that statement in terms of non-renormalizability of the theories without them. But another way of phrasing the statement that you need to extend your theory is to observe that really you have a breakdown of unitarity. And so here in gravity, it really, I think in some sense may be true that this unitarity issue is the deeper issue. And this whole story, and in particular the black hole information paradox, certainly seems to be suggesting that unitarity can be respected and restored, but at the price of locality. Okay, finally, there is this question of correspondence. Where does local quantum field theory plus general relativity break down? So let's think about a two-particle Fock space state, and it's more sensible to describe things in the context of gravity as, say, minimal uncertainty wave packets as opposed to, well, plane waves or things localized precisely at a point. And the question is, when does a local quantum field theory description of this state, when is it expected to break down? And so this should be a good description basically when these two wave packets are sufficiently separated as compared to the, roughly speaking, the Schwarzschild radius given by their center of mass energy. But when they become too closely spaced, then you expect this description in terms of local quantum field theory as I've been describing to break down, where G is some constant of order G Newton. So this is when gravitational effects in a flat background become non-perturbative, and we see evidence for that on shell, and plausibly this extends to an off-shell statement. And this basic parameterization has been called the locality bound. There are actually other versions of the locality bound. One can use the usual energy time uncertainty relationship to turn this into a measurement limit on time resolutions, for example. You can formulate an n particle statement that you expect for n particles. You have a breakdown of a local quantum field theory description, basically when the smallest, or the largest separation becomes too small. And also there's a statement along these lines in the context of de Sitter space when you ask what states of de Sitter space have a perturbative description that is good. So I don't have time to go into any of those in any detail, but let me just point those statements out. So a suggestion, which I think is plausible, is that perhaps these observations and bounds are special cases of some sort of deeper principle that states that physics actually is non-local when you must take into account the non-perturbative dynamics of gravity that unitarizes gravity, at least unitarizes in an appropriate sense, in domains where gravitational perturbation theory breaks down. And so, well, I think that's a very interesting question for the future. Of course, we have to understand non-perturbative gravity. We do have other hints of non-locality. There are other indicators, for example, from the basic ideas of ADS-CFT and holographic beliefs. Though I want to emphasize that so far we don't really have, from this point of view, a fully accurate way of addressing these basic issues. For example, formation and evaporation of a black hole is hard to study in this picture. Secondly, well, you could say, well, I know in field theory, locality is encoded in commutativity of local observables, but in gravity, we don't have gauge invariant local observables. You can ask how you ever recover anything approximately local, and there are apparently ways to do this in terms of this relational observable and proto-local observable story, which I talked about earlier in work with Meroff and Hartle. But the bottom line is you only recover locality approximately, and there are limitations, and these limitations appear directly related to the kinds of gravitational issues I've been talking about, the locality bound, and so on. So once again, you have tried to corner locality, and it has eluded your grasp. And finally, some of these conundrums of cosmology that we encounter in internal inflation, the landscape, Boltzmann brains, and so on, seem to be suggesting some breakdown of general relativity plus local quantum field theory. There have been a couple of recent papers on that, Arkani Hamed and collaborators, and then some work with Merrill, and a few observations in this paper as well, so I don't have time to go into those. But I think it's a plausible assumption that in certain circumstances, to be explored further, locality is not a fundamental property of physical theory. Certainly, we have had a hard time nailing it down. Well, what about our original problem, though? And that is the black hole information paradox. How is it actually resolved by some non-local mechanism? And I think there are actually two logical possibilities for what is going on with black hole information. If we think about quantum mechanics and how it emerged from classical mechanics, I think that's an illustrative possibility. If you think about the hydrogen atom, classical mechanics doesn't break down due to some intrinsic failure at the Bohr radius. It breaks down in the center of the atom. But we know that the correct story is, by the time we reach the Bohr radius, classical mechanics just isn't a correct description any longer. You shouldn't be talking about classical physics at that radius, and so you just forget about it at that point. So classical physics is replaced rather than breaking down. You could contrast that to other situations where physical theories break down, and that's how they predict their own demise directly and predict that there is some more complete physics that's needed. So these are really two logical possibilities. I think there's some evidence for B, actual evidence of breakdown, but I'll briefly explain what that is. So to understand that, let's start with the essence of Hawking's basic calculation showing information loss. So Hawking argues that the amount of information lost in black hole formation and evaporation is related to an entropy, and that entropy is computed from a density matrix, and that density matrix is the density matrix basically seen by an outside observer to describe a state on a space-like slice. Specifically, the space-like slice, and this is with sort of subsequent improvements over Hawking, you have a space-like slice that both goes through the exterior and interior of the black hole in a smooth and stays away from pathological places like the singularity, a so-called nice slice. And you trace over that to get a density matrix and then this missing information. And so that's the essence of Hawking's argument for information loss, with a little bit more explanation, which I don't have time for, but which most of you know. And the question I have in mind is whether we can really justify his argument in a reliable approximation. Specifically, it should be the leading contribution in a perturbative expansion in G Newton, or 1 over m Planck, say with fixed geometry, fixed mass of the black hole times G Newton. And so the question is, can we get out his picture, which is basically quantum field theory in a semi-classical background, in such an expansion systematically? Let's just ask this in the context of single scalar field coupled to gravity. And to be slightly more explicit, we might imagine computing this nice slice state in terms of a functional integral over metric perturbations and matter fluctuations. So you decompose the metric into the background piece plus the fluctuation piece. Likewise, the action breaks up. There's a classical term which I've dropped. These are the quadratic terms and the fluctuations, semi-classical terms, and their cubic terms and higher order terms, which are also higher order in the 1 over m Planck expansion. There's, of course, the coupling between the metric fluctuation and the stress tensor, which we're all familiar with, and so on. And so a question is, well, is this a good expansion? And in particular, are these higher order terms important or not? Hawking's original calculation basically is just using this semi-classical field theory in a classical background in order to draw the conclusion. And so one way of checking this is to think about, here's another picture of black hole geometry. Think about the effect of a small infalling perturbation. You could either drop some matter in, or since the black hole is evaporating, that's an approximately thermal process, there will be fluctuations in the amount of energy emitted. And you might have a fluctuation where the black hole doesn't emit a particle it should have, or emits an extra particle, and that just as well would correspond to an early perturbation here. And what we want to do is see if you have such perturbations in terms of the amount of matter, say, falling into the black hole, what is the effect of these 1/m Planck terms? Do they lead to important corrections? And so, in particular, we're interested in the effect of this perturbation on a late-time outgoing Hawking photon on the nice slice. I'll draw the nice slice shortly. And of course, here's the partner particle that falls into the black hole in the usual kind of picture of how Hawking evaporation works. And one observation is that late time actually is connected to this high energy limit I was talking about earlier, roughly speaking. You see this by taking this geometry and Schwarzschild time translating it. So watch carefully. So we're going to just time translate, and as we time translate, this fluctuation becomes higher energy and sort of gets compressed against the would-be past horizon. And of course, you drop this region of the space-time ultimately. So we've now time translated this late time fluctuation back to a now. And so let's look at the effect of this perturbation on the nice slice state. And roughly speaking, that's going to be given by the stress tensor of the perturbation times the Green's function, and then times the stress tensor acting on this state, the effect of this perturbation. And the question is that a big change in the state due to, again, these higher order corrections? There are various gauge subtleties in sorting this out. The earlier arguments I've given were based just on looking at the change in the geometry up here, but I think the really interesting and probably right way of looking at it is the change in the nice slice state. And since I don't have time to go through this, I'll just summarize the answer by stating that when you include these higher order terms in the 1/m Planck expansion, you estimate that there's an order 1 change in the nice slice state when you look at one of these nice slices at a time of order m cubed. And that's a very interesting time because, well, so that suggests that there's a breakdown of perturbation here, that the leading order terms get order 1 shifts by higher order perturbations. And that's an interesting time because this is the time scale by which Page long ago argued you would have to have information start to come out of the black hole if indeed that's the correct answer that it does come out. I should also, well, actually, before I do that. So this leads to a proposal for how the information paradox is resolved. First of all, Hawking's argument for information loss is, this suggests, not reliable, and to accurately compute the nice slice state and prove that information is lost, this suggests that you need non-perturbative gravity. So merely that statement tells you you don't have a paradox. If that is true. And then once you know that you don't have a paradox, well, you're left at least with a problem. How does the information actually get out? What's the dynamics? And that could be resolved if non-perturbative gravity, which is what we need to describe the process, actually has the appropriate non-locality. So I could supply more details, but really that would be another talk, and I'm almost out of time and almost done. Let me mention that similar considerations suggest that a perturbative treatment of the de Sitter space breaks down on a similar time scale due to large fluctuations. And this kind of argument is also related to some arguments given by our Hamid and collaborators in a recent paper as well. So some conclusions. Perturbation theory breaks down in high energy scattering at sufficiently small impact parameter, and it appears that that breakdown is intrinsically gravitational, and there is no obvious role for strings in the story so far. So it looks like if there is non-locality, it's quite possibly, and apparently it seems, intrinsically gravitational. Moreover, when you look at the black hole formation, well, actually the black hole evaporation question, it looks like perturbation theory fails when computing the information loss. I think this needs to be more carefully explored. There may be some way of resumming things to restore the validity of perturbation theory, but it's not clear to me yet how that would work, and quite plausibly it doesn't, but that needs to be sorted out. And so the overall suggestion here is that the non-perturbative gravitational effects restore unitarity, but at the price of locality. Of course, what really is needed here to fully study these processes is the non-perturbative and quite possibly, as I've argued, non-local dynamics, and we simply don't know what it is. And again, I'd like to raise this question, well, is it string theory? Does string theory really have anything to say about it? So let me just close by pointing out that it's fun and possibly helpful to think about an analogy, and that analogy is to the emergence of quantum mechanics, and I think the relevant time is pre-1925. So just to compare, of course, quantum mechanics was the story of h-bar. Now we're talking about h-bar and Newton's constant. A sort of basic paradigm system for quantum mechanics was the hydrogen atom. Now a basic paradigm system that we should be understanding is the black hole. We had in the formulation of quantum mechanics some very important paradoxes that guided us, in particular the ultraviolet catastrophes, and in particular the instability of matter appears to have guided Bohr quite significantly in formulating some of the foundations of quantum mechanics. Now we have a set of paradoxes, and I think one of the primary ones is the black hole information paradox. Before quantum mechanics was properly formulated, we had some information about how it worked in the form of the old quantization rules. Now we appear to have some similar things, like the holographic principle, the statement that the amount of information in a given region is given by its bounding area. And then we also have some notion analogous to the uncertainty principle about where the old theory appears to be breaking down and where it could be replaced by some new dynamics in the question mark. So comparison between the uncertainty principle and these set of things like the locality bound and this more general non-locality principle. Also, I just want to mention, of course, in today's physics, there's been a lot of study of extremal black holes. And you could ask, what's the parallel there? And I think, in some respects, it may be that these are a little bit like noble gases. Namely, that they're kind of complicated and highly symmetric objects, and they certainly contain the essential ingredients of the theory, but they're a little more obscured in that context. Just a thought. But what we're really after is both the kinematics and dynamics of the new theory, and of course that's where we really have a complete mystery, I think, at this point. Maybe string theory, but maybe not. And that's the sense in which we appear to be pre-1925. 1925 is, of course, when these things really began to fall in place. So I'll just finish by asking the question, what is this non-local mechanics, as it were? I think that's something we really have to work with. Thank you.
Any questions? Yes, Gabriela.
Yes, it's actually returning the question you asked me yesterday that I don't understand.
Good.
If you go back to those, I don't know if you can quickly go back to those
Yes.
diagrams.
You want the H diagram or something
Yeah,
else?
where you have the R versus Q.
Yeah. Yeah, one. Here we go. Oops. Oh,
So, my point is that the mere fact that this parameter R to the T becomes to 1 has not necessarily tell you anything about whether the series diverges, converges, or what. Right? It depends on the coefficient.
oh well, yeah. Okay. If they were
Suppose that the series has a finite radius of convergence, result of this parameter, given if there is some analyticity, given R is something like the energy, B is something like the angular momentum, there is some analyticity proof. So I think the real thing is to try to become the series, to produce all these three diagrams to kind of attach to the external layer. If we want to develop the effective, actually we did try to develop an effective field theory, different topologies, I think it's a very central point, but I don't think you can just argue the fact that the parameters are only one.
Well,
unless the limit of convention was really zero.
Perhaps what I was saying was a little too strong. Certainly, well, it's a very interesting question what happens. I think it's quite plausible. It does just break down. Maybe there is a way of resumming it. Certainly, at very small impact parameters, you're meeting first trouble.
Very small,
and
but the finite range of convention. Suppose the series comes up to log of this square minus R square. Then a large B should be just the ordinary log of this square. And the order Rx is developed in
but the thing is, if it did sum up, and if there is a finite radius of convergence, then that just tells you that you can get down to some impact parameter, and after that you lose control. So it would, in effect, be telling you. Well, okay, right. Yeah. So very good question, and it's mysterious what actually is going on here, but certainly there's indication that it's interesting.